Well, good morning, and thank you for attending today's College of Engineering Distinguished Lecturer Series. It is my great pleasure to introduce our speaker, Dr. John Sarrao. He's Associate Director for Theory, Simulation, and Computation at Los Alamos National Lab. Today's talk, have it right here, Opportunities in Mesoscale Science. His primary research interest is in the synthesis and characterization of correlated electron systems, particularly in actinide materials. John completed his undergraduate degrees at Stanford University and then earned a master's and PhD at UCLA, all in physics. Did some postgraduate work at UC San Diego and then in Florida at their National High Magnetic Field Laboratory. And then he joined Los Alamos in 1997 as a technical staff member. He's since held a variety of management positions as a leader of materials physics and applications, for instance, eventually rose to become director of the Office of Science Programs and of the facility called MERI, Matter, Radiation, and Interactions of Extremes, in Extremes, which is enhancing our understanding of materials in extreme environmental conditions. John won the 2004 Los Alamos National Laboratory Fellows Prize for research, in part for his discovery of the first plutonium superconductor, which revolutionized the field of actinized materials research. He's also recognized for momentous contributions to the field of strongly correlated electron systems. He was promoted to his current position on March 2013, and he leads Los Alamos Lab's efforts to apply science-based predictions to existing and emerging national security missions. Later that same year, he received the U.S. Department of Energy's E.O. Lawrence Award for the discovery and study of new materials, especially those based on plutonium, for advancing the understanding of unconventional magnetic and superconducting states in strongly correlated F-electron condensed matter systems. I think that's the quote from the... He has co-authored more than 540 publications, which collectively have been cited more than 13,000 times. Please join me in giving a warm Aggie welcome to Dr. John Sarrao.
Thanks.
Before we start,
yes.
I have
excellent.
gift bag.
Thank you very much. I appreciate that. Yes, no, thank you. It's certainly a pleasure to be here. I've certainly collaborated with a bunch of people here at Davis over the years, some of whom are in the room. But this is actually the first time I've been on campus in quite some time, so it's actually nice to do this, and I appreciate the opportunity. What I wanted to do today is talk about an activity that's called mesoscale science and give you a flavor of that. But I deliberately put the accent on the title on opportunities, because what I want to do is describe 3 potential opportunities, and hopefully everyone in the room will resonate with at least one of those, and maybe some people resonate with all 3 of them, and that'll be a basis for sort of future discussion and collaboration. And so what I want to do is tell you about the Office of Sciences, Office of Basic Engineering Sciences, view on mesoscale science. So there's a particular DOE report that I'll talk to you about. I want to talk about Los Alamos' perspective on mesoscale science, which is partially grounded in this facility that JP described called MARIE. And then perhaps most importantly, at least from the Los Alamos perspective, grounded in this broader opportunity in mesoscale science and grounded in this, our particular interest in materials and extremes, are there things that we could do collaboratively together? And so you know, I'll sort of strive to make this as much of a discussion as possible, and so don't hesitate to interrupt or ask questions as we go along. To try to keep track, at least for myself, if not for you, I'll deliberately try to do 3 talks all at once. And so the code is the templates will change. So there are 3 distinct slide templates in my presentation, and that's actually on purpose, not an accident. So I will talk firstly and mostly about this Office of Science report called From Quanta to the Continuum, Opportunities in Mesoscale Science, that I and my colleague George Crabtree helped lead for the Department of Energy. And much of what I'll say in that context is described both in the report that's shown here, as well as in an issue of MRS Bulletin a year or 2 ago. So that's, although I don't speak for DOE, at least the slides that look kind of green will be relatively DOE-centric. And so if you find nothing else that I have to say interesting, that at least points you to opportunities for collaboration and research agenda with the Office of Science. Then I'll talk about, from a Los Alamos perspective, where do we see our future in materials, which is very much in this domain of mesoscale science. And so to get there, that kind of comes in three parts. One, presumably like all of you, we read reports that DOE puts out and ask ourselves the question, are there research opportunities for us going forward? One of the things that we'll talk about a lot is this notion of codesign. And so codesign is a word that Los Alamos misuses consistently. So if you're a computer scientist, codesign means something very specific. It means the interface and interaction of software and hardware, of architectures and algorithms. And when I use the word, the way I'm going to describe it in a moment, in audience of computer scientists, they have a very hard time with the discussion because I'm clearly misusing a word that's important to them. They're right in their definition, but we use it this way anyhow. We use it in the sense of not just the question of how models and theory and informatics come together with computing and visualization, but we deliberately broaden it to include experiments. So one instantiation of that is, sort of like in the very generous bio that described me, most of what I do is experimental materials research. So why would a person who's an experimental material scientist lead a theory, simulation, and computation organization? In no small part, it's trying to bring those things together. And as we'll talk sort of in the second half of the talk, that particularly comes together in this facility concept called Marie, where we're trying to understand and predict and control materials, especially in extreme environments. So you take a broad-based Office of Science report, and you say, we have a particular interest in integration, because it's something we think we do well as a national laboratory, and we especially want to apply it to a set of materials and extremes challenges. What's sort of our take in that context? And so that's sort of slide template number 2 of 3. And then slide template number 3 are just the slides that I blatantly stole from Dave McCallan in the room. And so the question that we've been discussing with Dave is, how do we take Los Alamos' interests in materials in general, in mesoscale science more particularly, pointing towards materials and extremes, and how do we use that as a context for enhancing our partnerships with the various campuses of the University of California, most especially here in Davis? And so if sort of the story all holds together, there's sort of a broad science opportunity, there's our particular interests, and hopefully a place that will spill into the discussion of things we could do together that take the kinds of partnerships that have existed between Los Alamos and Davis through a number of years, and a number of institutes, and a number of pairwise collaborations into an overall collective where the whole is decidedly larger than the sum of its parts. And so if we can get that far, then we'll surely be successful, and we'll try to do it in about the next 45 minutes. So let's go back to the Office of Science perspective. And so the question is, what is mesoscale science? And so I'll deliberately never say mesoscale science is X nanometers or Y microseconds, because that's not the point. What's the point? The point is, imagine the ability to manufacture at the mesoscale, where if you sort of read the bullets of the slide, the ability to do directed assembly, and it's a bit confusing whether you're talking about top-down assembly or bottoms-up assembly. You're just making material come together that have function you can't otherwise imagine, and doing that effectively. If you look for places that you could, that's been done before, biology is an awfully good inspiration. So Mother Nature is awfully good at making materials that function effectively and display chemical transformations that are impressive. How do you do that sort of artificially rather than biologically? And if you can do that where you're blurring these boundaries of top-down and bottom-up, you can make very direct technological innovation. And so while I won't give you a sort of specific definition, the ability to accomplish all these things is the promise of mesoscale science. And so that's a fairly attractive, I think, definition when you're talking to staffers and the like. The question is, can we take it to the next level of science and talk about what the directions really are? So let's spend a few minutes on that. So again, I won't give you a definition. I'll continue to resist the temptation of defining numbers the entire presentation, because that's entirely not the point. But it's clear that there's a limit. That's the quantum mechanical limit. That's the isolated atom limit. That's the limit of simple and perfect and homogeneous solids. And that's a limit that we understand pretty well. There certainly are open questions in that domain. But we can write down the fundamental equations, and we sort of put them in textbooks, and we can describe that fairly effectively. And there's a limit that looks a lot like the real world, where the fact that h bar is not equal to 0 doesn't matter so much. That interacting collective phenomena definitely occur. And while interesting functionality emerges, it tends to emerge in systems that are complex, that are decidedly imperfect, and that are heterogeneous. And so this crossover from quantum to the continuum is what this mesoscale opportunity is all about. And so we'll spend some time talking about both the attributes of that regime and what success looks like in trying to control it. So importantly, this is not sort of any sort of repudiation of nano, because much of nanoscale science over the past couple decades has been the question of how do you work in a reductionist way down? How do you go from understanding very bulk-like systems working down to sort of fundamental building blocks like chemical bonds and periodic lattices? And it's only a consequence of the success we've had in trying to understand unit processes that we can get to fundamental building blocks and then begin to work our way back up in a constructionist way to try to understand phenomena that make a difference. So nanoscale science and mesoscale science are very much coupled. And in fact, trying to understand things on sort of the rising edge here actually forces us to ask deeper questions about how well we understand the fundamental building blocks and how we put them together. And it's that challenge, it's that pivot that really is central to the kinds of mesoscale science phenomena that we'll talk about. So that still may be a bit sort of high level for someone striving for a definition. So let's talk about a few specific signatures of mesoscale science. So mesoscale phenomena tend to be dominated by situations where atomic granularity starts to matter less. So if you're in the very atomic quantum limit, the notion of counting how many specific atoms you have or what the particular character of their chemical bonds are is a meaningful consideration on this scale. As you sort of move from the quantum to the continuum, atomic granularity starts to fade away, and these kinds of structures, which are certainly important and certainly functional, but their atoms aren't necessarily countable, is an important part of that transition. The individual position and presence of atoms matters less. Another way to think about it is in terms of energy quantization. In the very small limit, you get to very large energy scales and well-defined levels in simple harmonic oscillators. If you ask the question, where does that crossover happen from well-defined separated energy levels to an energetic continuum, it tends to happen, and this is about as close as I'll get to a quantitative definition, on energy scales or temperature scales that are about room temperature. So when you're in the fuse of nanometer regimes, you're not really quantum mechanical purely. You're also not in the continuous bulk. There's this interesting regime where atoms are losing their particular signatures and energy quantization stops mattering because energy scales and temperature scales you can readily access can easily change the state of the system from one limit to another. On these same kinds of scales, that's where collective behavior begins to arise. So it's not a question of how does a single atom behave, and if you have 10 to the x single atoms, that their behavior is just a multiplier of the same thing. They begin to form collective states that matter that's not just a result of finally dividing the material. So collective phenomena is a key signature, as is the notion of interacting degrees of freedom. So it's not just a question of a system that's strictly an electrical response or a magnetic response or a structural response, but they all become coupled in various kinds of piezoelectricity or multiphoric behavior and the like. And so in some sense, the previous definitions were largely a question of what's the relevant scale. I think both of these speak to the opportunity, because you can imagine designing systems on the mesoscale where you can have multiple degrees of freedom giving you multiple functionalities all in a collective sense. If you can get design control on this scale, you can really yield the kinds of materials that imagine the promise of mesoscale science we talked about a few slides ago. And so the opportunity becomes very rich when you get to this space. Similarly and importantly, this is a regime where defects matter. When all you've got is a single atom, by definition, everything is perfect. Once you get to this intermediate scale, defects matter, fluctuations matter, statistical variation matters, and those aren't bad things. If you want to get to high-strength materials, it's not about how do you make a perfect system, because in most cases, a perfect lattice is actually not very strong. You get much higher strength by controlling defects and manipulating them. If you think about superconductors and how much current you can carry, the current carrying capacity largely comes from the defect structure, not the perfect structure. Sort of hand in hand with the importance of defects and statistical variations is the role that heterogeneity plays both in structure, but especially in dynamics. So again, there's a multiplicity of timescales that come to the fore to play out in this regard. And so it's those now 6 hallmarks we've talked about that begin to frame, in a more technical sense, this vision of mesoscale, this vision of an opportunity space between the quantum limit and the continuum limit. That's a relatively rich environment that I would say, whether you're talking about the domains of chemistry or condensed matter physics or material science, we're beginning to understand, we're beginning to control. We're basically smart enough to be dangerous, but we're not nearly solving the problem. And so it's an interesting area to go focus on. So it's those characteristics that this Office of Science report that I described talked about. And if you then take that a step further and say, okay, fine, I'm beginning to appreciate there's a regime here that's potentially interesting. Can I go focus on some specific areas that can go yield progress and making progress in those directions? This is a particular articulation of that. So I won't read these to you, but I would hope that across these sort of 6 particular directions, whether you come from sort of a chemistry background or material science background or a biological background or an engineering background, you can appreciate the nature of those kinds of problems. The vocabulary kind of embraces the challenge we're talking about, and you can define well-defined research directions that say, I can make progress in my particular field by, let's pick randomly, trying to focus on transported dynamic response by manipulating the structure of the mesoscale. So think about electrical energy storage, for example. The catalytic response that occurs on surfaces, the charge transport, is definitely dominated in those regimes. And you can talk at a pretty deep level about specific opportunities in each of those areas that are a consequence of the particular directions we talked about. And so that's what this BES report talks about. And this, I think, is where the Office of Science is interested in investing in the years to come, and we'll talk about that more in a moment. So let me give you a few examples of the kinds of things one's talking about. And I'll be deliberately biased towards synthesis, because I think the ability to actually make these kinds of mesoscale structures and architectures is a regime that we're not particularly good at, and there's lots of gains to be made. And so what this slide tries to articulate is to say, well, if I'm trying to build something that's sort of, from the atomic level up, you can think about, how do I take a couple of atoms, put them in the right place, hope bonding occurs. If you're trying to do sort of directed assembly, you've got a whole set of questions like, what are the structures I'm using to template them? How do I get to fundamental building blocks that are relatively complex and relatively complicated? And how do I bring them together in assembled structures? And this is a case where the complexity of the slide is deliberately on purpose, because the principles that give rise to these kinds of assemblies are much more complicated and require a variety of degrees of freedom to come together, that if you can be successful, you can become very effective. But understanding how to manipulate these systems is very much a grand challenge. And so it's, how do you build structures in these ways that accomplish the ability to get where you want to go in these regards? Similarly, you can think about manufacture at the mesoscale. So more or less, how we build a lot of structures is we say, well, let's start from a bulk. Let's chip away at it. Let's shape it. Let's form it. Let's get to some structural functional unit. But in fact, there's much more one can do in this regard to put together a variety of architectural structures that have a variety of functionalities. And the question becomes, can you bring them together to do it simultaneously? So again, a good example in the domain of superconductivity is there's actually a healthy industry using coated conductors to conduct electricity. The best structures we have today have 5 or 6 different sort of functional elements. Instead of saying, how do we make it good, we say, well, we need this to carry the current. We need this to inhibit corrosion. We need this to give it some strength. If you can bring all those pieces together in one thing, you can make dramatic progress in that regard. And so it's all about, how do you bring the various building blocks you have in an effective way to move things forward and make progress. And so and to do that, you not only have to be able to make stuff, but you have to understand from a modeling perspective and a measurement perspective what you're doing in that regard. So again, another example of competing degrees of freedom is certainly how you think about light and matter coming together. So it's not strictly independent structural systems, but the dynamics of photonic crystals and surface plasmons and metamaterials all give this interacting degrees of freedom sense that both gives you very deep scientific challenges, but also the ability to impact energy technologies. So I've tried to give you a flavor of sort of a broad class of problems that try to sort of embody these sort of mesoscale principles we talked about that hopefully touch on areas of activity you've thought about. And so the question becomes, how do you go make progress in this regard? And so I want to come back to this notion of co-design a little bit, and we'll continue to return to that over time. I would assert that if you're going to make progress at the mesoscale, whether you're talking about the physics of the mesoscale science, the material science, or the chemistry, that it's a wholly unrealistic approach to just say, I'm a synthesis person. So I'm going to make some stuff, and maybe I'll find an experimental colleague, and maybe he or she will do some measurements. And if the two of us get stuck, we'll find a theorist and say, can somebody explain my data? That's a pretty inefficient way to get stuff done. If you want to tackle the kinds of problems we're talking about, you really need a holistic interaction of synthesis and characterization and theory and simulation all coming together. So that the things that I'm making tomorrow are grounded in calculations my colleagues did that were based on models tested by data taken the day before. It's that seamless integration that really comes together in that regard. So it's one thing to say integration is important, and it certainly is. It creates opportunities for collaboration. But it also raises the question, do we have the synthesis tools and the characterization tools and the theoretical and simulation tools to address the kinds of problems we're talking about? And the answer is kind of, sort of, probably. That again, we know enough to be dangerous, but these are not solved problems. So let's talk about where we are in synthesis and sort of how one moves things forward. There certainly is one aspect of that what I've talked about before, which is how do you do sort of the fundamental building, the actual science of synthesis? How do you get matter into the structures that you want that you can build the kinds of architecture shown here? And again, it's awfully hard to see, well, there's an atom and a chemical bond. These are pretty complicated engineered architecture, engineered structures that give you the function that you want. So one aspect of it is the science of synthesis. The other aspect, which I think is equally challenging, is sort of the science of function. So it's not a question of how do I create some structure. We talk a lot about sort of processing to performance, but if you could skip the whole structure-property relationship and just go straight to function, you could make great strides in that regard. And a number of the things we're interested in are very much in the regime of competing interactions. So it's how do you realize the function you want through structures that are relatively complicated and are relatively interesting. So it's a pretty deep challenge for a synthetic person. And again, I would assert you can't possibly get there without a set of computational tools that are not only predicting materials and their lattice structure, electronic structure, but also predicting their functionality by design. That becomes a very deep part of the opportunity. And at least in every case that I can think of, the ability to observe and control the synthetic processes in situ is at the very least a significant accelerator for progress, and it's probably a requirement for progress. To just say, I'm going to go make something, after it's all done, say, is it any good? How do I change it? That's just not very effective. If you can say, well, I'm understanding how these structures are building up, and I'm understanding their local susceptibilities and local dynamic responses, I can optimize the process on the fly to move myself, whether I'm talking about a functional phase diagram or a structural phase diagram, I can move myself around in that space becomes a deep opportunity. So fortunately, especially in the domain of Office of Science, they've actually built a large number of large-scale facilities in recent years at the LCLS in the Bay Area, at Brookhaven, the National Synchronous Light Source 2, at the Spallation New at Oak Ridge. Large-scale tools are available. So again, we know just enough to be dangerous. We have the tools we need to do something, but are we really using them effectively to address the challenges we're talking about? I think, again, the answer is kind of, sort of, not quite there. So we have the sources we need, but we still need work in both how you do the optics of the measurements, the detectors, creating the sample environments to do what you want to do. Because again, mesoscale science is not about pristine, sort of clean table perfection. It's about systems working in real time in the real world. So you need advances in all those things. And if you're successful, you've got an enormous data handling problem. Because you've got to understand what are the various variables that matter. What's the environment in which the material is performing? How quickly you're measuring it? What kind of things are you doing in that regard? And so there are significant challenges in how one thinks about in situ, in operando measurements, especially when you're interested in multidimensional defect evolution. Because again, there's not very many perfect structures to be found in this space. There's a pretty deep opportunity here. One of the interesting challenges in this domain is, we think about time-resolved measurements, and at least for me, we often think about how do you go faster and faster and faster to stop time. But there are a class of phenomena in the domains of degradation science and materials aging and sort of chemical blurring out that making long-duration measurements becomes very interesting. And you can't make sort of a lifetime measurement on timescales of years a femtosecond at a time. So you have to be smart about how you sample things in that regard. Again, if you're interested in sort of beyond perfection, diffraction is a very powerful tool, but you also need to move towards imaging to understand non-periodic structures, and chemical spectroscopy is a key. And so measurements that allow you to do all of these things together, especially in time-dependent ways, becomes very important. And again, if you can do all of this, you've got an enormous amount of data on your hands. Whether you can use it intelligently or not becomes part of the challenge. And so again, progress is being made, and as is often the case, sort of progress foreshadows even deeper challenges as one looks to the future. And so finally, and certainly not last in the set, is sort of the set of challenges in theory and simulation. So certainly mesoscale science resides in this intermediate regime, but it's almost surely not the case that just a question of passing parameters from ab initio atomistic scale models all the way up to the macro scale gets it done. There are interesting questions about sort of thinking about the mesoscale as a nexus, and both what do you need from the atomic scale and how does that translate to the bulk scale, that becomes an interesting challenge both in terms of fundamental model development and how do you do that in the space of simulation with community codes where, if different people are using the same algorithms and codes, they ought to get the same answer. And if they're getting different answers, that's adding ambiguity in the space. And that's a common characteristic of what's going on today. All right, so I've tried to give you a flavor of both synthesis and assembly challenges, characterization challenges, and theory and simulation challenges. And all of those are manifestly hard problems. But in point of fact, the real opportunity is actually doing all of them simultaneously. The examples of how do you simultaneously do synthesis and characterization theory as we talked about? How do we take multi-step processes and do that in a way that's interactive and constructive across a variety of scales where you're actually getting to a place where theory is guiding simulation to design functionality. So it's bringing those things together that's part of the opportunity that, again, I think is not something we've done to date. We've built a lot of these tools at the nanoscale, but we've not actually deployed them for these class of problems. And so there's a clear integration challenge, which also points to a collaborative opportunity. So it's certainly the case that the word mesoscale science is not new. People have talked about mesoscopic science for some time. There was sort of a resonance of mesoscopics in the 70s. Hopefully, what I've told you is convincing that this is a different opportunity than the kind of sense of mesoscopic physics people focused on some years ago. But nonetheless, it's important to ask the question, why now? So why now is a twofold answer. One, because there are really hard problems you'd like to solve, problems that sort of capture the imagination of mesoscience in the beginning that we can't quite get to. But we're actually at a pretty good place. We're able to both develop first principles models and implement them as simulations in computers that can actually simulate the scales that we're talking about. So again, you have enough of the tools to be dangerous to actually tackle real and important problems. We've learned an enormous amount about the fundamental building blocks of chemical bonds and perfect structures. And we've developed tools that allow us to understand those that let us move forward on these kinds of challenges. Oops, sorry. And as good as we're getting in this regime, we're sort of both trying to understand complex materials we can't understand, and we're beginning to synthesize them in ways that we sort of want to understand. They come together that says, it's a pretty good time to get after this problem. That there are both problems worth solving and scientific frontiers worth pursuing that make that important. So let's talk about, sort of to wrap up this section of discussion, if you want to be successful, if you want to sort of embrace the opportunity, what do you need to go do? And again, this points to this Office of Science report where there are sort of specific investment priorities for trying to understand how you develop lab-scale tools, not just at large-scale facilities, but in individual investigators' labs. That's an important part of driving the frontiers. how do you use these large-scale facilities well and develop the means to do interesting measurements that are complicated in that regard? How do you get a set of measurement scientists that do these kinds of things well? And very importantly, how do you grow a set of people who sort of think in this regard? So if you've embraced sort of the challenge of mesoscale and you ask yourself the question, well, is it a condensed matter physics problem? Is it a solid-state chemistry problem? Is it a material science problem? Is it a materials engineering problem? The answer really is none of the above. And so if you're sort of grounded by people who are sort of in a particular disciplinary vein, you're not going to seize the whole opportunity. And so there's a need to grow a set of people who haven't been have been colored by, I grew up being this and that's all I do, and embracing the broader opportunity. That's a key part of the challenge. And as good as that can be, there's also a huge opportunity for building collaborations of experts to span the whole problems. And so as we'll come to at the end, a large part of our interest, especially in these discussions, is how do we do these kinds of things well? So I won't, this just kind of talks to some of the gaps that exist in terms of interdisciplinary science, in terms of a focus on synthesis, in terms of focus on multimodal measurements, the kinds of gaps that exist that I think are interesting research opportunities that can both foster a generation of scientists and point to opportunities to have broader impact going forward. And so I think it's a ripe area, and I think it's an interesting possibility. And so I won't repeat myself, but if you sort of think about sort of the discussion of the last 20 minutes or so, I think it's not overstated to say that in the mesoscale, there really is discovery opportunity for finding phenomena we have not previously understood. That if you think about how you think about foundries in a different way of sort of directed assembly, you really can get from going from structure to property to actually designing functionality that really can drive a set of technologies. And so the good news is, I think it's both a technically grounded message and it's a message that sponsors seem to understand. So there seems to be a fair amount of congressional interest in moving in these directions, and that's something that BES is focused on going forward. One representation of that is shown here. So one of the things that the Office of Basic Engineering Science did back on the 2007-2008 timescale was they did a grand challenge report. They said, what are the decadal challenges for materials and chemistry research in this area? And that was 2007, 2008. They decided sort of last year that, well, that report's about a decade old. It's time for a refresh, because most reports in most directions are good for about a decade. Let's go do a study and call it Grand Challenges 2.0, which is about the worst possible thing you could do. So they didn't actually do that, but they felt challenged by their nuclear physics and high energy physics and astronomy colleagues. So we went and explored that, and it turns out that I have a role in this activity as well. And what's come out, and so it's still, sort of, it's a question to the community whether this particular tree metaphor works or not. It's sort of a source of strong debate at the moment. But the point being that there are transformational opportunities for discovery science that build on the original grand challenges. So from the point of this discussion, what's the point? If you go back to 2007, 2008, these red phrases are sort of the buzzword descriptions of 5 grand challenges that BES defined at the time. Those were very important research directions. I would assert they still are. And if you look at them, they have a very atomistic, very nanocentric flavor. And so clearly on the time scale of 2007, 2008, the question was, how do we get to the end of this reductionist path downward? How do we define those fundamental building blocks, those key unit processes? If you re-ask the question today, what arises are the top 5 here. There are 3, and there's really no direct coupling between this study and the Mesoscale Science Report. But this is a much more meso-friendly vocabulary. And importantly, in this report, there was sort of a discussion of these are great direction, and oh, by the way, tools are important. And I think the biggest mistake of that 2007 report was the appreciation that tools, that method development, are far more than just a means to an end. They're actually very much research directions. And so this report is still playing out, but what it will fundamentally conclude is that all of this is ripe opportunity space. And I think it's one instantiation of this opportunity that mesoscale science presents going forward that I think will color VES's research agenda and sort of solicitations for many years to come. All right, so we're going to switch slide templates, and now we're going to talk about Los Alamos' interests, which are very much a mesoscale science, but from a slightly different direction. And so this facility that we're talking about is called MARIE, which stands for Matter, Radiation, Interactions, and Extremes. And so a simple way to think about it is, if you take this broad understanding of mesoscale science, this sense that it's not just about perfect structure, but that microstructure matters, a set of challenges exist, and you think about the challenges at Los Alamos that we face in terms of building a set of components that have to perform when asked to perform, how does that problem translate in that direction? So don't have to say this, because this whole notion of that we're going from making observation to controlling properties has been sort of the root of the discussion of the last part of time. If you ask the question, and again, got emerging tools and simulation advances that make it possible to ask questions about length and timescales we've not thought about before. So I think that should be fairly intuitive, at least from the previous part of the discussion. But if you ask the question, what's the unfinished business? What's the work that still needs to be done? Clearly, you need an ability to do in situ dynamic measurements on time and space scales that matter. You need to do that on well-controlled and characterized material. So you have to very much couple the synthesis and the characterization. At least at a place like Los Alamos, we're pretty interested in extreme surface environments, things under extreme dynamic loading, things in radiation environments, both because that's where our mission exists, but I'd say more broadly, because it tests our understanding. It's one thing to say, I can predict how a material will behave in ambient conditions. It's a whole lot different to say, I want to take it to a different regime and see how it does in that regard. And again, if you can't couple this all simultaneously in this misuse of the word co-design, you're not going to be effective in that regard. So this is sort of our parallel thinking over the past, again, about a decade in trying to move things forward in this direction. And our vision is to build a facility that does that. So we work for NNSA, so we have a very clear and specific national security mission. We do more than just general sort of science, which is deeply important to us. And so what I wanted to do was try to translate these sort of mesoscale science questions to direct mission challenges for us. And so I would say it's not so much a question of whether you have a particular interest in sort of Los Alamos' core national security mission, but ask the question, how do these questions of mesoscale science we're talking about play out in that context? So the basic challenge we have is that we have a stockpile that we built over the last 20 or 30 or 40 years. We've not done a full-scale test of the system in more than 20 years, and we have to have confidence it's going to work. Because if you choose to use the systems, you want to actually have them perform or you have a problem. And so if you walk through that, and in fact, if you don't just ask us, if you ask our sister laboratories at Livermore and Sandia, what's the key challenge we all face? The key challenge is that the gap in our ability to predict and control materials and devices to manufacturing processes is especially urgent. We don't do that particularly well. If you translate that into a set of challenges, it basically boils down to how do you understand dynamic materials performance? Again, a regime where microstructure matters. It's one thing to say, let's take a continuous homogeneous solid and subject that to some load. That's fairly predictable. But in heterogeneous microstructure defected solids, understanding dynamic materials performance is pretty hard. And in fact, process-aware manufacturing is comparably hard. And so this is a discussion that's played out sort of over the same period where additive manufacturing has become very much in vogue as an important direction. The whole key really comes down to how do you manufacture things in a process-aware way? If you change the processes you use, can you predictively understand their performance? We have a long history of saying, well, we're going to make things in similar ways. We're going to do an A/B test, and we're going to see if they're the same. And the A/B tests are never quite the same. We ask ourselves the question, well, how is A and how is B different? And we come back with, I don't know. And you're kind of stuck in that regard. And so those challenges are directly important to us. But what I would argue, I urge you to think about is they're also applicable to a broader set of challenges more than just our particular mission suite. And that becomes part of the collaborative opportunity in this space. So again, we've convinced ourselves, which may be more honest than we should be, that we really don't have an adequate predictive process-aware understanding of materials performance. We we can make stuff, we can go test it, we can see how it does, but there's a huge opportunity to be more predictive and more process aware so that when you want to change processes, when you want to go from a casting process to a wrought process, when you want to go from a sort of traditional formulation to an additive manufacturing process, you can do that in a way that's predictive because that opens up an enormous amount of design space for you. So if you think about what you need to do in that regard, there come down to sort of three critical challenges. One is, how do you validate models that transcend scales? So one of the things we do is we have to predict how materials will behave in regimes that we can't test them. So how do you make those kinds of certification decisions that say, given what I know, I'm going to say that it's going to work? Our traditional approach has been, well, we've made it a certain way, and the process is very controlled. So if I make it exactly the same way, then everyone after that will behave in the same way. And that's a perfectly reasonable way to do that. The problem becomes, what if you lose your ability to make it the same way you've always made it? Then you're kind of stuck. What if you want to change something? Then you're kind of stuck. This kind of predictive modeling becomes very important. If you can do this, you can then change how you think about what the qualification standards are. So certification is about saying it will perform as I want it to perform. And qualification goes to, what are the things that I have to do? So it's not a question of, do it exactly the way I've always done it. It is, if I can produce a material that has this density and this microstructure and these other attributes, it doesn't matter how I got to that point. I can predict its performance going forward in that regard. And that's a key challenge in doing that. And perhaps most importantly is, the most important thing for us is having a set of people who can make certification decisions and qualification decisions. And the best way that we know how to do that is to give them hard problems and test them. Because there's a very weird balance of, when you've designed a big integrated experiment that's going to work and it doesn't work, it's a very sobering reality to say, maybe I'm not quite as smart as I thought I was. And the flip side is, there's a paralysis in being able to take risk. And so the ability to sort of train people to say, we're going to take all these individual pieces, and I want you to make a collective judgment whether it's going to work. Testing people on hard problems is the best way we know how to do that. Through the history of the Manhattan Project through to sort of the present, sort of the whole underground nuclear test program was very useful in that regard. And people both got very smart and very sober what they knew and didn't know. We need to fill this gap going forward, and that's a key part of the challenge in that regard. So these are, I think if you read this, and you've been listening for the last little bit, I think there are very strong overlaps between the broader mesoscale science directions we're talking about and some of our key mission challenges. But there's a definite bias both in the types of materials and the kinds of questions we're trying to ask, which I think gives Los Alamos a particularly different slice across the challenge of mesoscience than other people might think about in that regard. So let me give you two examples to try to make this real. So both of these are experiments that we'd like to be able to do that today we can't do. So this is the microstructure for material. And what happened was a shock wave came along here, bounced off this end, came back, and it failed in this black thing here. So we know that it failed. We couldn't really tell you where it was going to fail or why it was going to fail. But you'd firstly like to be able to, and this measurement gets made basically in an electron microscope doing serial sectioning, which is an important direction going forward. You'd like to be able to do this in real time in 3 dimensions. So what does it take to do that? Well, so now imagine some solid that's being subjected to a shock that now, instead of doing these serial sectioning 2-dimensional cuts, you're doing this in the 3-dimensional bulk. And you want to do that so you can actually understand where the shock wave is, how it's propagating, where failure is beginning, where it's beginning to emerge. You probably can't make failure go away, but you probably can engineer when and where it's going to happen. So this cartoon begins to describe the attributes of a measurement that would actually let you do that. That becomes the definition of a facility you'd like to go build. Perhaps most importantly, if you can't model and simulate the dynamics you're talking about, then there's really no point in thinking about the experiment. If you can't sort of do this coupled synergy, you're just not going to be making progress in that regard. This is an example of sort of structural materials behavior. The point here, it talks in a different example about a sort of a functional materials example, where the point is synthesis is a dynamic materials performance process as well. So the high explosives we use turn out to be among the least homogeneous things you could imagine. There's high explosive crystals, there's binders, there's stuff. And we know that certain batches are really good and certain batches aren't so good. And that's OK as long as you get enough of the batch you like. But when the batch you like kind of runs out, then you have a problem. So again, what this cartoon tries to depict is to make an effective high explosive, you do need chemical synthesis understanding that plays out both in single crystals and in sort of formed polycrystalline materials. How do you build that up? How do you actually watch while you're synthesizing it these multi-layered structures? And again, we don't have the tools to do these kinds of measurements, but we're beginning to be able to model both how you form these materials and how they behave. That's part of the measurement opportunity. And so the advantage of thinking about a facility that doesn't exist is you can actually ask the question, how can I try to do what I can't do today and build up the methods and the tools and the means and approaches to do that, not just say, I'm stuck with the best tools that I got. Can I make progress in that regard? So again, to this point about co-design and being smart enough to be dangerous, which is an opportunity and a challenge, I want to talk for a minute about sort of the bridge between mesoscale materials and simulation and computation. So one way to think about the problem is to say, well, if I think about how many atoms I can simulate, for example, in a molecular dynamics calculation, and how long in time they can run out, the kinds of phenomena we're talking about, the domains of where sort of microstructure formation, where nucleation and void coalescence come about, are in time scales and spatial scales that are about the scale that we can compute today. So it's a necessary but not sufficient condition that you can simulate a system that's large enough that its attributes can be mesoscopic in character. If you can't get there, then there's no point in having the discussion. But the real opportunity becomes, how do I actually understand that in a way that you're varying the physics? So it's a common practice today to do what we call adaptive mesh refinement. So we say, how do we change the resolution of our models dynamically so we put more resolution in more interesting regimes and less resolution in less interesting regimes? And that's an important advance. The next step is to take that to what's called adaptive physics refinement. How do you have better, more faithful physics models at the shock frontier where you're doing mean field models further away? It's the dynamic evolution not only of the resolution, but also the fidelity of the models that becomes a challenge in this space. Because when you can do that, you can directly couple to both the functional synthesis examples I talked about and the structural materials response example I talked about to bring those things together. And so again, it's not an experimental thing or a theoretical thing. They all come together to try to address these challenges. So that sort of is the long-winded definition of how one thinks about co-design. So I think all of the mesoscale science problems we've tried to talk about really aren't about isolated synthesis or characterization or theory or isolated domains. It really is, how do you bring together in a coupled way things that can make progress to actually give the ability to predict and control materials behavior? I think we're making steps in those directions. Much of the energy around things like the Materials Genome Initiative are trying to define fairly simple structures. Hugely important, but still an enormous amount to get done to work in this mesoscale science regime. And so, at least from our perspective, it's a rich opportunity, both in the general mesoscale science sense and as we think about structural materials in particular. All right, so that sort of brings us to sort of why this discussion and how do we move forward. And so I'll go back, switching slide templates again and going back to stealing from Dave. As we've talked about it, I believe there's technical opportunity here. I believe there's research direction from us, Los Alamos, going forward. We certainly have a tradition of partnership with Davis and various other UC campuses. The question is, how do we take the conversation further? So it's one thing to sort of come out and spend a day and talk to people and give a seminar. Is there an opportunity to sort of have a workshop that builds on a set of discussions that takes sort of the short 1-hour seminar to a broader dialogue to say, what are the key research agendas that we see common cause in moving forward? I've talked in a number of places about the importance of what we'll call the mesoscale pipeline, a set of people who are trained differently across synthesis and characterization and theory, who are trained across disciplines to advance frontiers that are very deep. You can pick a subset of logos of UC campuses from our perspective, each is different and complementary, and that's important. And so we would imagine a partnership with Davis that's similar but different to one with Irvine or San Diego or Santa Barbara or Berkeley, because I think those are the kinds of things that give us particular relationships. And I think if all goes well, that creates a broader thing that not only says, from a Davis perspective, hopefully it'd be nice to have a more enhanced Los Alamos partnership. But if we can also be a catalyst for broader relationships, not only sort of with us in some sense, but also with other sister institutions, that's value as well. So the question becomes, does the science opportunity create a collaboration context to sort of move things forward and address the kind of challenges we've talked about? All right, so what have I tried to convince you of? I've tried to convince you that mesoscale science is an important science frontier. I think there's clear evidence that that's where the Office of Science is going. That's where NSF is going. I think it's an interesting factoid from the Office of Science perspective is something like 40% of the proposals they receive today now use the word mesoscale. Whether that's because people have actually embraced the vision of mesoscale science or they just know that the way to win proposal competitions is to use buzzwords is not something I will comment on. But in a fairly short period, that at least piece of jargon has moved forward. Maybe there's substance behind it. So hopefully that's interesting and illuminating. I've tried to convince you that from our perspective, it's not just a good idea, but there really is mission imperative. And we ground that mission imperative in this facility vision we call Marie. So as I've told you, Marie is an unbuilt facility. You might want to come use it. It'd be nice to say, well, you can use it next week, but we're a little bit ways off from next week. We're probably sort of a decade out from actually building it. But again, that's an opportunity because that says we're going to be in this game for a long time, both in terms of using the facility to do science, but also in defining it makes it an interesting time to partner for something that we're going to stick to over a longer period of time. And I guess the question on the table that I'll finish with is, can we leverage this opportunity to broaden partnerships that already exist between Los Alamos and Davis and take that to the next level? So with that, I'll stop. I'll thank you for your attention and be happy to answer questions. So questions? Yep.
It's a very challenging task.
Yep.
And there has to be change from silo-type education
Yep.
to interdisciplinary education.
Agree.
Currently, we don't do interdisciplinary education, we do collaborative.
Agreed.
One guy from physics will come in. So there is and the second thing is you have to attract very bright people.
Right.
I don't know how will you assure that because it hasn't happened.
Right. So I agree that it's a very hard problem. I think your framing is right. I think when people want to make steps, they go from say collaboration to joint mentorship. So I'm in Department X, you're in Department Y. We share students. In the best cases, that works well. In the majority of cases, it doesn't work so well. So I don't have an answer, but I think it's an interesting question to ask. Can the national laboratories help sort of reframe that question in a different way? Can your students partnering with a set of us help broaden that envelope? Because we've got to find a way to get there, and our traditional approaches are not working nearly as well as they need to work. Because it's exactly as you say. So I think everyone agrees that single discipline is passé. We do things that aspire to be interdisciplinary, but they're really only multidisciplinary, and multidisciplinary doesn't get there far enough. And so the question is, can we, the labs, play a role in helping you guys do that? Because it's a very important and key challenge.
Thank you.
Yep. Warren?
Can you give us a broad update on Marie, what the facilities will be, what the procedures, activities
Yeah.
that are different than what we've been doing?
I'll give you two answers. So one is, in project space, the way that DOE builds facilities is they decide that a mission need exists. That turns out to be called CD0. Marie will get CD0 this year in all likelihood. The next step is what's called CD1, which is alternatives analysis. So I'll answer your question, but it has to be caveated by there's lots of technical studies that say, how do you best get there? So if what you want to do is understand microstructural evolution in 3D solids on timescales that matter, it is our decided opinion that to do that, you have to have a source of photons, because there's only enough fluence of photons to get that done. those photons have to be high enough in energy that you can probe the kinds of materials that weren't like actinides. The source has to be brilliant enough to get the dynamics right. And coherence is a huge advantage when it comes to doing both diffraction and imaging. So all those considerations taken together give you something that's like a 40 kilovolt X-ray free electron laser. That's several times the energy of, for example, the LCLS-2 that Stanford is building at the moment. So it's complementary in that space. It will simultaneously do an X-ray free electron laser and a proton radiograph to give you both density measurements and structure measurements. So it's a multimodal measurement that does not substantially exist. And it will have intimately coupled to it synthesis, lab scale characterization, and theory. So someone like you really could be making suggestions today of stuff that I could make tomorrow that we could diagnose together at the large scale accelerator complex. That's the vision that comes together. And that fits into a box that's moving through CD0, funded by NNSA, sort of as we speak. And probably opens for business in the early 2020s, early to mid 2020s. There's one back here.
Thank you. I'm over from geology.
Uh-huh.
I came here to ask you a specific question. If you could tell me about some of the tools, especially computational tools, that you've developed for understanding the structure and the dynamic structure, so how these small mesoscale materials like tiny crystals or metamaterials evolve as you're synthesizing them. I think there's an opportunity to take the tools that you've already developed and apply them in geology.
Right.
For example, I think a big unsolved problem in geology right now is what is going on outside of equilibrium as rocks are formed.
Yep.
In igneous petrology, we don't really understand what sort of textures you get in a rock. The relative size, shape, orientation, trace element, chemical gradients, they're all there, and they say something. And if we knew what they were saying, we would be able to tell exactly what temperature and pressure regime the rock traveled through as it was being created.
Right.
I think that something that would be very useful is a way to basically take data sets about the distribution of the elements in a rock, or the distribution and shapes of crystals in a rock, and get sort of the statistical information of what the crystals look like, which crystals are growing off which crystals, and how big they are, all of that.
Right.
But we don't yet have a way to do that except visually.
Right.
Where, as a geologist, what tools are available to do sort of similar things in your field?
Right.
How do I find them?
Yeah. So firstly, I think your intuition is correct. There is synergy to be had there. And so at a set of the light sources and neutron sources that I talked about, and I can certainly give you specific references, there are geoscientists working to solve these kinds of problems. I think you're also right that statistical analysis becomes very important. But the other part that I think that geosciences teaches us in particular is rare events matter. Right? So there's some fluctuation that was created that causes things to go off in some direction, different parts of phase space, and those are rarely, so they're very much dynamic, time-dependent measurements, but it's not about femtosecond evolution. It's about on some multi-decadal time scale, some slow evolution happened that took us in some direction. That's very much part of the space, and so there's actually in this report. There's a fairly decent description of some of the geoscience challenges in this space, and I'm happy to sort of give you a card afterwards and point you in the direction of some of the facilities. Yeah. Yep. Other.
So I'm working with transport of biomolecules, so I've got to use a mesoscopic model for that, and for example, lattice bolts.
Yep. Right.
And so what I use is espresso for my molecular dynamics code. You said there's a need for more widely used and well-curated codes.
Right.
What do you think those could be based on the ones that are available now? Do you think one needs to be completely newly created, or are there ones that you see promise in now that could be those well-curated?
So BES is actually running a competition sort of literally as we speak to do, at least in materials design space, some of those kinds of things for functional materials at the moment. So since there are proposals that we're part of, I know exactly which are the best ones to do. So I won't actually answer that question. But what I'll say is, I would say it's a blend of people taking codes that exist and saying, I have a good MD code, I have a good electronic structure code, let's marry them together to do lattice electronic structure simultaneously, is one class of proposed ideas. And another class is to say, let's take, say, electronic structure and take it to the next level by adding correlations to it. So it seems to be a step too far to both say, let's take the next generation of the code models that I have and add new functionality to it. People are either merging multiple separate things or taking things to the next level. But I think it's a rich opportunity space, and I think BES will spend real money in the near term to do some of that. Go ahead.
I'm interested to know what kind of mathematical tools you are thinking of to take account of this interaction between the multi-levels and formulations. For example, like averaging techniques or homogenization techniques. I mean, are you interested in these things?
Yes,
I mean,
definitely.
what are the mathematical formulations? I want to see equations to get answers.
Right. And so I think, so people are, so yes, we're definitely in the mathematics of this. People are actively working both in terms of materials research and computational algorithm research to do that better. Because there are serious inadequacies in the approaches we're using that, to go to the geology example, miss sort of the evolution of rare events and how do you predict those.
References to that?
Yes, absolutely. So both in this report and so the discussion. So in this report, which is not yet published, but there are versions of this. There's a sort of a talk that describes this. The mathematics is very much described in this space, and I can certainly point you to the right direction in that regard. Because you're absolutely right. With that, the right algorithmic and mathematical tools aren't well used by the broader chemistry materials community to make progress in that regard, and you have to do that.
Maybe one last question? No? Well, let's thank our speaker once again.
Thank you all.